9.3. So in 9.3, we're going to finish up the idea of tailored polynomials. I think this section is actually misnamed. I don't think it's about tailored polynomials. I actually think this is about error. Error. Okay. So let's start with this idea. I would like to find a polynomial that estimates the value of sine of x on the interval from negative pi to positive pi. And I'd like to do so, with an error of no more than
1 million.
I don't think that says 1 million. I think that says 1/10,000.
1/10,000. Yeah. Oops.
Okay? So that's what I would like to do. How do I do it?
Well, you have to find out where sine converges. Don't you? Then you can make your chart.
Use the calculator.
Okay, well.
By the way,
let's
I'm
see.
not going to be nearly as helpful on this one as I'm going to
Okay,
been
sine
another
of
one.
x.
Because you already know a lot about sine of x.
Sine of x, we already know the Taylor polynomial.
Okay?
It's every
Yeah, so it's x minus x cubed over 3 factorial.
Right, plus x. Sorry, minus x cubed.
Where does it convert?
Minus x cubed over 3 factorial. I don't want you to go ask the question, where does it converge?
okay
Okay?
plus x to the 5th over 5 factorial, and so on and so forth.
Okay? My question is, at what point can I stop building out this polynomial and still be within 1/10,000th of the real answer? Can I stop here?
No,
How do you know?
I guess.
You have to find the real answer.
No, you have
Well,
to find an answer that has an
I
epsilon.
think it's a great idea. The real answer. Well, there's an infinite number of values that sine has on that interval.
Do sine of pi. Well, no.
Why sine of pi?
Because the answer is 0.
That is true, and that is helpful.
Doesn't work.
Sine of pi is correct, but not for that reason, though.
Oh, okay.
Because the outside you have to make it at least that far.
Bam.
Nice.
I want to go with that idea a little bit further for me, then. Because the further we get from the center, the more the estimated polynomial strays from the real. At exactly the center, the function and the polynomial are exactly the same. Sine of 0.
Oh, because you generate the polynomial from the center.
Right.
That's how you get it. So.
Okay.
Okay.
So when you're at the center, all except the constant terms go away. When you're at the center, the function and the polynomial are exactly the same. As you get further from the center, the more the two start to break away. If we were looking for a place where the error is worse, it's going to be at pi or at negative pi. Let me say that one more time. The error is going to be the worst the farther we are from the center, and the center is at 0. So at either of these two extreme values, we think that's where error is worse.
Okay.
All right?
So we want to get as close to 0 as possible without getting to 0.
Well, okay.
No,
so yeah, 'cause the sine of-
I want to find how far I have to go to make sure that the error anywhere on that range
Okay.
is less than 1/10,000.
Well, the sine of pi is 0. So,
I'm going to write that down. Sine of pi equals 0.
so if you really want to use pi, I mean, I'm confused because you're going to have 0 minus 0 plus 0 minus 0.
No.
I'm telling you right now, there is no error. These two things are exactly the same at 0, when x is equal to 0. I don't want to be at the center. I want to be at pi. So what I want you to say is sine of pi is 0, and then
you
if
got pi.
if I call this P7,
Okay.
P7,
Why don't we do P90? X.
The order it's the order to the 7th because it's the 7th term.
okay, and I would say P7 at pi
Minus
is equal to
3.15.
pi minus
Pi cubed over 3 factorial plus to the 5th over 5 factorial minus
Multiply
pi
by terms
to the
to get
7th
zero.
over 7 factorial.
And I want to know, is this value really close to 0?
I have no clue.
Yeah,
No.
Let's find out.
Let's find out.
Are we calculating or no?
Yes. I'm certainly not going to take the 5th power of pi in my head.
Oh, you can do that?
I know
Well,
the fifth power.
I know that I'm
People are always
I'm
like, I know pi to
no-
100 digits.
I'm no Brian Lackey, so it's like okay. So
What about the Rachel?
No,
Carter's
wait,
sister knows it to like 250 digits.
should we do this?
Yes.
Okay.
Yeah.
We shall.
So pi
Minus pi
Minus-
cubed.
pi
To the 3rd divided by
Cubed.
3 factorial.
divided by
3 factorial.
I'm just gonna write down 6 because I don't want to go into the menu.
Plus
Plus
pi to the 5th
pi to the 5th,
divided
Divided
by
by
5 factorial.
which is 120,
Minus pi to the 7th over 7 factorial. 4.
Ugh.
We gotta go further.
Okay. No, that's a small error. It's less than 1/10.
Yeah.
But if we took this value and went one more term out, if we added another term onto this, would it be minus or plus?
Plus.
Plus, you're good.
Because the
Excellent.
seventh term is a minus, so the next one's going to be a plus. Pi to the
9th
ninth.
over 9 factorial. Correct.
Nope.
Gotta go further.
But the error did go down. By the way, typically with the errors, we don't look at their pluses or minuses. We look at them as simply the absolute value. We're about 75 hundredths off here. We're about 7 hundredths off there. I look at the absolute values of the error, or of those differences. Ready? Okay, so let's minus pi 11th.
Over 11 factorial.
Yay! We're not there yet. We're about 300, 10 thousandths off.
Okay, because this is 0.0004. And we need 0.0001. So do one more? How's that look?
It'll be plus
Plus.
Pi to the
pi to
13th.
the 13th over 13 factorial.
There should be a shortcut for factorial.
On the new calculators, there is.
Probably, that makes sense because you've been doing a lot of calculus. This is the only time we ever
Okay.
used it, really.
Hooray! We're now at 0.0002, which is less than 0.0001. So we had to go to the 13th level to get this value low enough. Why did we do this example? Because first of all, we've got to get this intuition that the error, the difference between a function and its polynomial representation gets bigger as we get further and further from the center. All right? That's the big idea here. Because at the center we're exactly there, and then the differences get exacerbated.
I know, but the further we are from the center, we get a closer summation to the actual value, right? Because
Okay, when I say further from the center, I'm referring to the fact that this Taylor series is centered at 0, and that the error, or the difference between P7 and the real function is going to be, well, let's say, we'll do it like this. At A equals 0, no error. or sorry, at x equals 0, no error. At x equal pi, great error. And in between here, less error.
So we care about the value of x.
We care about how far x is away from the center of the polynomial. All right, let's try another stab at big idea. Now, first of all, I got to explain what the word truncation means. Truncation means to lop off. Okay, typically, you have been either told to round off your answers to the hundredths place.
Now you're truncating.
If you don't look at rounding, you are truncating. You simply lop off the extra piece. When we look at a function, and in this case, the function that we are looking at is 1 over 1 minus x squared. When we look at that function, and we take and write this polynomial, we have truncated the Taylor series to get that polynomial.
Okay.
Okay?
So we've been truncating a lot of lines.
Yeah, but we just never used that word before.
Not gonna-
What are the new words today?
Right? So here is a function. Here is its truncated
All right, let's do
Taylor
that.
series, which we'll call a Taylor polynomial.
Let's do it at 1.
And I would like to know, what is the approximate error on the interval from -1 to 1?
Well,
How badly could this polynomial be off from the real answer?
I wouldn't think it would be that bad. Yeah, you can. What? Oh.
If we were going to try to do the real, not real answer, you would try 1, and if you did that, you would put in 1 minus 1 squared, and you get something undefined.
Okay, fine.
So that's
Zero.
Why do 0? It's the same.
No, 0 at the center. The polynomial and the function always are the same.
Limit.
Oh yeah, limit.
Okay,
Bam.
hold on. Let me make sure I get that idea. This series is centered at 0. How can I tell?
Because of the x, otherwise.
Because it doesn't.
It's right in the middle of -1 and 1 is the number 0.
No, no. 'cause-
Well, okay. If that was an interval of convergence, which it is, then indeed you would say it's because 0 is right in the middle of there. How about the other thing, that Taylor series are C0 plus C1 x minus a plus C2 x minus a squared plus dot dot dot.
There is
That's because there's no A.
other value aside from
There's
that.
no A. A is 0.
There's no A.
Okay, so I can look at here and see there's no minus thing. A is 0.
Okay.
All right. So you want to take the limit.
It's
Okay.
getting intense now.
You know what? If I got really close to 1, perhaps we can see what kind of error would happen. Ready?
So when we get
No, hold
really,
on, hold on.
When we
Ready?
get really close to 1,
Really close to 1.
F
What
of
if I
x
was at
approaches infinity.
0.9999?
F of x approaches infinity.
Is it equal to infinity at 0.9999?
No, it approaches it.
Let's see. 0.9999 squared. You got calculators. What are you waiting for? What's the value of this function at 0.9999? He says it goes to infinity.
It approaches.
Approaches infinity.
Can never go to
Unless you're
Unless
He's-
you're what?
Chuck Norris. He's counted to infinity.
What about Buzz Lightyear, dude? Come on.
Twice.
It goes beyond infinity.
What if it approaches infinity?
5,000.250001.
Yeah, there you go. It's approaching infinity.
5,000
Well, you can't approach infinity. It has to.
5,000.
Wow.
Tack another 9 on there. See what happens. I
No,
dare ya.
Actually, what I would be
I
interested
double
in,
dog dare ya.
Gotta do it.
what I would be interested in is what would happen if in P6 I put in 0.999. What do I get?
Let's find out.
1 plus 0.99 squared.
It should be infinity. Though. You know,
squared plus 0.9999 to the fourth plus 0.9999 to the sixth. What do you get?
Nowhere near close.
Nowhere near close. Because this is like 1, and this is real close to 1, and this is real close to 1, and this is real. I bet you that this is going to be a little bit under 3.
Yep.
That's what
No,
I'm
it's
guessing.
actually a little under 4.
9.988.
What is it?
A little bit under 4.
9.988.
A little bit under 4?
That's the calculator
Because
says.
it's
Yeah.
1 plus 1 plus 1.
Yeah.
Oh, a little bit under 4, right.
3.8.
3 point what?
9988.
9998.
9988.
Now, Katya,
It's
that doesn't match your intuition,
It's
does it?
still gonna approach infinity because you constantly add them. Wait, are you just talking about those 4 terms or like?
Oh,
You fucking-
yes. But you hit upon the most salient point
Truncation
here.
error.
Did you hear what she said? If we kept on adding on to this, the stuff that we don't have here, the 8th term, the 9th term, the 10th, sorry, the 8th term, the 10th term, the 12th term,
5,000th term, which is what there was.
those things are missing, aren't they?
Yeah.
Yeah. They're missing.
They've been truncated.
They've been truncated. So here's what I'd like to do. Now that we realize there's this huge difference, at least between this 4-term Taylor polynomial and the real answer, I would like to look at this problem again with fresh eyes. Right? Eric, you're writing something down. Because I'm going to erase a bunch of this stuff. All right? Great. Here's what I'm going to write. I'm going to write that 1 over 1 minus x squared is equal to 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus x to the 10th plus x to the 12th plus dot dot dot. And I am going to call this part P of 6. Taylor polynomial order 6. Right? And when we lob off all that red stuff,
You two are.
you know what I'm going to call this? I'm going to call this the error.
Massive error.
That's the stuff that's keeping us from having P6 be the right answer. We'll call it the error.
They're bigger than.
Are you okay with that idea? You know what? I also want to call it another name. Ready? Not only is it the error, it will also call it R6.
Oh.
R4
R2 and R6.
Remainder?
for remainder. Exactly. So you have the polynomial and you have the remainder. And the stuff that's in the remainder, the stuff that didn't get added on, is the thing that's keeping you from getting exactly the right answer. Now here you go. Are you ready?
Yeah.
We can actually, in this case, calculate exactly what the error is for some given value of x.
Sigma. No.
Subtract.
Oh, I could write this as a sigma. Sure.
Well, I'm just thinking of ways you can do it in the
I
calculator.
could write this as sigma as, I don't know, as n starts at 1 to infinity,
Why did you put 1? Why can't you just put
x to the 2n plus 6.
Or you could put down there n equals 4 and start and put down the nth term for that.
Or I could look at the remainder portion. Okay, by the way, I want you to see here that remainder 6, the 6 has to do with what's left over after you've gotten the 6th order polynomial. It's everything left. They don't call it remainder 7, even though it may start with the 7th term.
Okay.
All right, that's just a little. Or we can look at the the red series. And we could say that red series is a geometric series.
The red shift.
It starts with a value, and the next term in that series gets bigger
By x.
by
2x squared.
x squared. So this R6 is geometric.
Oh, it's geometric with a x to the 8th and r x squared. And so you put it one.
Hold on, let me get that written down so everyone else can see it. With a x to the 8th, because that's the first term in the series,
And r equals x squared.
and r equals x squared, because every term beyond there gets bigger by x squared,
And so then
which
you do
means
what
that
we
R6 is exactly
did, x to the 8th over 1 minus x squared. Nice. Okay. Cool. So
Oh,
then we
wait,
can
wait,
plug that
hold
in.
on.
Absolute value.
Yeah, well, no, that's what the R is. The absolute value of that we'll call the error.
Okay. So then cool.
Okay? Now, what happens if you do 999 or
To the eighth.
0.9999 to the 8th divided by 0.9999 squared? What kind of number do you think you get out of there?
Something like 4,000 something.
997. No, 96.
Are you sure?
Well, what he's doing is like, what did we get when we found the value of this function at 0.999? It was like 5,000 and change. What did we get? What did we get for the real value? Or sorry, what did we get when we did these first four values? 4.
I got something like
4,000.
5 thousandths.
What?
What'd you get?
I got 4,996.25.
Now, does that make sense? Remember, we said that when we did 0.999, this was 4. This is everything else. What did we say this was at? At x equals 0.999? 5,000 something. Yeah.
Can we know what order will give us the answer? Like P sub what?
Piece of what will give us a tolerable answer, an answer that's good enough at some error. That's what the rest of this whole lecture is all about. Are you ready?
Hold on.
I don't think so, but let's do it anyways.
I keep not getting the right answer. I don't know what's
Are you
going on.
getting a 9?
Are you putting the 1 and then 0.99 in parentheses?
So 0.9999, so that was my x, and I just
Okay, that's a good idea. All right. And so what we're going to say is x to the 8th divided by quantity 1 minus x squared.
that's exactly what I just had in there.
It's because I used my finger. When you use your finger, who knows what's going to happen.
That's literally what I had in there.
Right?
No, but it's actually literally what I had in there.
Because, I mean,
This is
from,
him,
from the
and then
information I
2
know right now, I
on
can guess it's the 9,999.
It's the exact same thing.
So I'm going to build this idea a little bit differently than you're thinking about it right now.
Did
So
you know
what-
the
I think I know what you're saying, but we're going to build something that's a little bit more general. So, okay, you guys ready for the next stuff?
Yeah.
Okay, here we go. Big beige box, which is always fun to look at. Okay, idea, theorem. Taylor's theorem with the remainder. So let's say we have a function. Let's say it has a Taylor series that can be written for that function. And let's say we know all the derivatives in some interval I. So I'm going to draw that out, what that looks like. I've got an interval I, and then right smack in the middle of it, let's put A, the center
If f
value.
has derivatives of all orders in an open interval I. All orders, so like,
That means I know the first derivative, the second derivative, the third derivative, the fourth derivative. I know all the derivatives for this function on that interval. For example, on sine and cosine, we know all the derivatives ad infinitum, right?
yes.
Okay, for e to the x. We know all the derivatives of e to the x.
Yeah, of course.
Oh yeah. Okay, those are what we're kind of talking about.
And what about like x squared? We know all those. All
Sure,
those
we
even
know
though
all
it doesn't
those
go to
too.
infinity. Okay, cool.
So this would apply to this as well.
Okay, for each positive integer n and for each x in I.
Okay, so no matter where we choose to truncate the p-series, so we get p sub n, the Taylor polynomial of nth order, no matter where we choose to truncate it, so for each positive integer n, so we're stopping at n, and that of course leaves a remainder of r sub n. We've got this very peculiar property.
I can't copy anything.
Okay, well, how about I let you copy and then I'll talk. How's that sound?
So that's just the f of a
Yeah, I'm
plus
recording it too, so.
the f of a plus f prime of a times quantity x minus a plus f prime of a over. That's just the Taylor polynomial.
This is the Taylor polynomial, right?
Okay, so yeah, I don't need to write that down.
That's why I called it p sub n.
Is that a plus sign underneath those right before the r sub n? Yeah, that
Yeah.
plus sign. Cool.
Because we're adding on the rest of the terms. So maybe r stands for rest.
Do we mostly use these equations in like programs? We like programs to do functions.
When it says f to the n plus 1, it means the n plus 1 derivative.
So indeed, this is the n plus 1 derivative of the function at some value c. So we have a in the center. We've got x, which is something in the interval. And we've got this new value c, and c has to be between a and x.
Was there anything between f to the n of a over n factorial times x minus a to the n and r of a x, r sub a sub n x?
At the minus.
I couldn't really tell. Thanks.
I don't understand. I
No,
didn't understand.
Between the r sub n x and
And this?
No, where
Yeah.
you drew the little.
Yeah, there's a plus sign.
That's
okay.
a minus.
There's
No, it's a plus sign.
It's a plus sign.
Okay, thank you.
Because it's the first n terms of the polynomial plus all the rest.
Okay.
That's where it's at a minus.
Why would it say minus? All the other ones are plus.
I don't know. I don't know.
Yeah, that's
Are
right,
you
you
ready
don't
to
know.
actually start talking about this?
Yeah.
Okay, so you've got all the notation down. Now let's talk about what this means. Now we know
This is the LA.
that when I do this much of the series, I get an estimate of the value of f of x. And we know that r sub n is the rest of it. If we left it off, it would be the remainder, it would be the error.
Okay.
Now this theorem says this really wild idea that the value of the rest of it can be thought of as the next term, not the rest of all the terms, but just that one single next term where c is the value you're getting your derivative from. And C, its restriction is it has to be between A and X.
That's wild.
That's really a crazy idea. But it's really, really powerful. It's like, I know that there's stuff that's missing. And that stuff that's missing can be summarized with the next term and just one special value, the location of the right place for the derivative.
And it always works.
It always happens that that's true.
That's
Now, from a practical standpoint, us finding what C is really hard. And we're actually not interested in finding out what C is. What we're interested in doing is saying, what does this help, how does this help us when we're trying to figure out what happens at the ends of these series about convergence and divergence? And how does this help us find out something about the nature of R of X, which I have been using synonymously with, it's the error. It's the stuff that's missing. Our calculators, when let's say they're doing sine, they don't add up an infinite number of numbers to find the values of sine. They eventually stop.
Shame.
Can this formula inform them when they can stop and still get a reasonably close answer?
Yeah.
So, there's one other usefulness on useful part of this, and we're going to use this to actually show that the power series for sine converges everywhere. All right? I'm gonna cheat. I'm actually gonna look at the book while I do this because I want to make sure I do it well. All right? Okay. So I would like to use this theorem in conjunction with this question. We have the power series here for sine of x. Can we show that this series converges for all values of x? Now to do this, I wanted you to think about this part of the problem. I want you to think about r sub n of x as n approaches infinity. Well, let's start by what we just defined r of n to be. R of n, we said, is the n plus 1 derivative at some number c multiplied by x minus 0, which I'll just write as x, to the n plus 1 power, all over n plus 1 factorial. Isn't that what we said in the previous slide? There's some value c between a, in this case 0, and x, which is someplace anywhere.
As n approaches infinity.
As n approaches infinity.
Plus 1. But that's the last derivative.
That's the next term after our truncation. Except for this isn't, that's at our center. That's a special number
I
c.
thought we were going as n approaches infinity.
I am.
It's starting off from wherever we left off, essentially.
Okay.
Okay.
Okay. So we would c naught. Sorry. Let me do this. This is equal to.
I'm just
sine.
confused because the n approaching infinity and the f of n plus 1. You know what I mean?
We know this part, right?
Yeah.
And I get up here.
Wait a minute. Isn't it
No,
x
this
minus
is
x
cube.
cubed
This is
over,
sorry. This is
Yeah.
cube.
and nths to the
and
fifth.
these are cubed, and this is a fifth, and this is a fifth. But we go in here and we get those first terms, right? We call that p sub n. And again, what are we saying? There's an r sub n in there which represents everything else. The error. What if the error goes to 0 as n goes to infinity?
Makes sense.
You know what that means to me?
What?
It means that the series has got to converge. There's no longer any difference. It goes to a particular value if the error goes to 0. Okay. Now, so let's look at this expression, which we said is equivalent to r sub n, and let's look at it.
I'm just
As-
a little bit confused about the n plus 1 because I thought, okay, we'll probably get to it. We'll get to it. Never mind.
So,
No, we said on the previous slide that this r sub n is equivalent to f of n plus 1 c x a minus to the n plus 1 over n plus 1 factorial. That's
the
what we
only
said on
thing
the
I'm
previous
wondering
slide.
about is how you're going to take the infinity derivative of c.
Well, I'm gonna for this
Right, right.
particular
We're gonna
function
get
we're gonna deal with that.
so what we're finding here, we're finding n, then I have to find what order would give us like the best estimation of the answer.
Okay, now this is no. We're gonna do that. We got two things that we have to use that remainder theorem for. First of all is to show that this is convergent everywhere, and then later we're gonna use it to find out what kind of error we get when we truncate at particular spots. So I got two items that we have to deal with this.
Is it always converged to 0?
If the function converges everywhere, yes. Okay. So here's what I need you to think about. What happens when n goes to infinity for this part?
Should go to 0.
Goes to 0, goes to infinity. Goes to neither.
So
Wait,
what I'm
our,
thinking is if you
wait, our function is sine.
Stays between -1 and 1.
It stays between
keep
negative 1 and 1.
theorem,
Okay.
Yeah.
We know every single derivative of sine. It's either sine or cosine or negative sine or negative cosine. No matter what it is, this little doodly job is somewhere between negative 1 and 1. There's not a lot of variation in it. How much effect is this going to have on our limit?
Not much.
Nada.
That's what
Now,
is-
here's where we get to the meat of the problem. X to the n minus 1. It's going to get really big, isn't it? N plus 1 factorial as n gets big. It gets really big.
Which one gets
Who
bigger
gets
faster?
bigger
Who
faster?
gets bigger faster?
L'Hopital.
Oh,
No.
Can't do L'Hopital in this case. See if you can figure out why.
Because you can't derive it.
Can't drive what? It. I hate it.
You
Factorial.
can't derive
You can't
infinity.
drive factorial.
Oh.
Why?
How's the
Because it's an integer function. It's not a
It's not a
It's not a
function.
continuous function. We don't drive anything except continuous function. You can't use L'Hopital. But we can talk about who gets bigger faster.
My bigger faster.
Okay?
I'm a graphic.
You're going to graph it?
I'm looking at my bigger faster notes, you know.
Okay, well, here, let me get the
The
calculator
bottom
out.
gets closer
Whoops.
to 0.
I don't know, man. I
If
don't know.
it reaches 0, the top spot grows faster.
Okay,
If it reaches infinity,
Ryan.
the top grows faster.
Give me an x. Give me a value for x.
Depends on the x, I say.
69.
6.
82.
Why?
Okay,
Oh, why not?
1002?
69 to the power of
18.
50.
Solid.
Big number.
Yes.
Okay? It's a big number. But the equivalent number would be 50 factorial on the bottom.
4. Not as big.
Not as big. Wait.
Now let's crank
But
up
what
the
happens
end.
what happens as n gets bigger?
Let's crank up the end.
69
to the 5,000.
No, that's going to take a while.
How about I go to the 100? to the 100th. Oh, overflow. Can't do it on that calculator.
That's not a calculator.
This just makes me
Can
want
it
to
do
have a better calculator.
everything? Like, is there
Oh, where's
overflow
my other
on-
calculator?
Is there overflow on the other one ever?
Is there overflow on? Well, how about we find out?
Let's do it.
This is gonna be ridiculous.
Okay, so let's bring up the CAS and see if we can do that. So we tried 69 to the 50th, and it was big.
Let's just do it.
50th factorial, 50 factorial is big, but not big enough. But the question is, as those n values get big, will factorial eventually overtake x to the n?
No, I don't think so.
What? Let's find out.
Well, because here's why. Here's why. The nth term, the nth factorial only has n number of terms. So if you have 100 if 100 is your n, you only have 100 terms, and each time you multiply,
Okay, I'll tell you what. You can't see all the digits there, so let me get an estimate of that.
That's a big number.
each time you multiply, you have a smaller number to multiply by. But when you've got it to a power, like here you're multiplying 100 terms. It's always going to be smaller because you're multiplying 100 terms here and you're multiplying 100 terms in the other one. But
how about wait? Think about it this way. So you're saying right here is 100 terms, right? And this one's going to be 100 terms.
But that's starting at 100 and that's starting at 69, whereas before one was starting at 50 and one was starting at.
And then guess what? If I go 69 to the 200th, I'll go 69 to the well again. I got to do estimate, but 200 factorial.
Wait, you can scroll over and like follow.
I could. And now all of a sudden factorial is bigger. So what's going on is both of these things, 69 and 200, is 269s. But here's 200 numbers, and some of those numbers are bigger than 69.
So I bet that at n equals 100, what would happen when n equals 138?
Okay? So 138. 138.
That's 168. 160. That's
Wait.
69 times 2. 69 times 2.
Okay, so you want n equals so you want 69. Yeah, you want 69 to the power of 138.
Yeah.
And then I want control approximately. And then you want 138 factorial.
Yeah. Do it.
Oh,
No. Come on.
Oh,
so I think you're reasonable guess. It doesn't work out exactly the way you're thinking, but you get the right idea. But can we disagree that eventually, when factorial gets much bigger, that it's multiplying the same number of numbers, but some of them become so much bigger than the base number 69 that it's going to get bigger eventually.
Mm-hmm.
Yeah.
So are we right to assume that in the case of factorial will surpass the top term?
That is correct. Given a large enough n, eventually factorial is going to overwhelm anything in the form x to the n.
Is there anything that can overpower?
Factorial?
Never.
Times factorial.
X cubed.
Actually, I think x to the x goes faster than factorial, or n to the n goes faster than factorial.
What about x to the n?
No, in fact, we have to know that's true, because let's say 138 factorial. That's 138 times 137 times 136 and so on.
N to the n.
But 138 to the 138 is the same number of numbers, but every single one of those numbers is, or all but one of those numbers is bigger.
Right.
So n to the nth goes faster than factorial, but factorial always goes faster than x to the n.
Can we see if it overflows ever?
And the answer, we did this in the earlier class, and the answer is yes, it does. So like 500 factorial.
Overflow.
It's just
Actually, 500 to the power of 1,000. will overflow. And we
Yeah,
actually
I've
did,
had overflow
we actually did that in the class, the other class. And so what we did when that overflowed,
Wolfram Alpha.
then we go to Wolfram Alpha,
Oh God.
Did it overflow?
and Wolfram Alpha never overflowed.
Really?
Well, they're running on big servers.
They have server farms.
Oh yeah, and
Do
so
1,000 to the 1,000th power to the 1,000th power to the 1,000th power.
well 1,000 to the 1,000th.
Do it again, and then do it to the 1,000th again.
Well, how about this? Even better, 1,001 to the 1,000th power. Chugga 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 chugga.
More digits. More digits.
Okay, and there's
Give
still
me
and
the
there's still-
digits.
But the big thing is when you're getting in numbers this big, what really matters is the order of magnitude. It's 10 to the 3,000.
Oh yeah.
Okay, the Inspire will overflow at 10 to the 999th. The TI-83s, 84s will overflow at 10 to the 99th.
What are the actual digits of pi?
We don't have that much time.
They don't? Would they have it though?
Obviously.
Not to an infinite amount of
How much
precision.
should they keep supplying?
Couldn't it keep calculating
It is left as an exercise for the student to find.
See a pattern in the numbers.
All right, so our debate here is that since factorial will eventually overtake x to the nth, this thing that represents the remainder
Goes to
as it
0.
goes to 0, and therefore the piece of n part must have a finite value. And there we have it, a roundabout proof that the sine function converges everywhere.
Okay.
All right?
So, anyways, like I was saying, we should have it in class work day tomorrow.
Okay. Now, finally, the stuff that Z wanted to look at. Now that we've looked at this relationship between the idea of remainder and error, and we can see that we can look at what happens to remainder over time, we have this general idea. If we calculate, or the remainder for a Taylor theorem, based on the Taylor theorem, the remainder has to have an upper bound. Now, there's a slight variation. We're not going to get onto the examples that use this, but there's a slight variation from the way Finney DeMano Waits Kennedy approached this, and my old book, the Stewart book, approached this. Okay, I actually would rather you not write this down, but rather write this down. Okay, so I'm going to simplify things just a little bit. It says that the absolute value of the remainder, in other words, the error, how far that we're possibly off from our function, has to be smaller than m times x minus a to the n plus 1 power, divided by n plus 1 factorial. It looks a lot like Taylor theorem. The only thing I haven't told you is what's m. Right? M is the maximum value taken on by the n plus 1 derivative on the interval I. Oh, we never define I. On, well, actually I'll say for values between
Betwixt.
I was going to just say that.
A
I was thinking about that.
and X. You guys read Shakespeare?
No, I just, like, I was thinking about it.
Oh,
Okay.
dude, every day. My dog.
Okay.
Something.
And then we'll apply this idea to say, okay, if I stop here, what's my error? What's the maximum? What's the maximum that the error could be? It doesn't tell you what the error is exactly. Why? Because if we knew the error, we'd know exactly what the value of the infinite sum was. But it does give us an idea of how close we are to the real answer. It can't be any worse than this. All right.
So long, future calc students.
Right. Yeah, there's no homework. There'll be homework over the weekend though. Don't you worry.
Would you like?
Hold on, I gotta shut off the recording.